Hello student, welcome to the session. As per your request, I am uploading some important named organic reactions which you are requesting since long, and these named reactions are quite important for JEE mains and advanced. Before our examination, I shall be trying to complete all these named reactions which are quite important from the point of view of JEE mains and advanced. So today I am taking up a topic of Malaprade oxidation, which many of you might not be knowing it as with the name. The reagent for this is called as periodic acid. Periodic acid is the name of the reagent which is used for the Malaprade oxidation. This particular reagent is mainly used for glycol splitting. As the video would go in detail, you would get to know what is glycol splitting and things like that. Along with it, I do ask you at the very start of this particular session, do you know anything about Criegee oxidation? Many of you people might be knowing the reagent, but you might not be knowing the name of this. This particular oxidation came into existence in 1931, and as a matter of fact, for Malaprade oxidation, this somewhere started in 1928 and got the endorsement in 1934. This is what you always have to remember, that in the historical background is always good to have a bit of discussion on the historical background also. So in this particular topic, we will be discussing that these are some of the questions which I come across in last 2-3 weeks. This is another question where HiO4 is being asked, and then there is another one where is this green colored compound is being treated with HiO4 and the things are being asked around it. And one more question which I came across is in terms of more than one question. So these 4-5 questions we are going to address in this particular video. So first, let me discuss about what exactly do I mean by periodic acid HiO4. Here the iodine is in +7 oxidation state. So as a matter of fact, this is a strong acid because the periodate ion is quite resonance stabilized, and it's also a good oxidizing agent because the iodine is in +7 oxidation state. It try to go into the lower oxidation state. So as a matter of fact, what exactly is the bonding aspect into this? This is the bonding aspect, and periodate ion which I am talking about is somewhat like this. When you deprotonate it, the H positive goes out and you left with this particular entity, and this is quite resonance stabilized. So this is a quite a strong acid, as well as it is a strong oxidizing agent because the iodine is in +7 oxidation state. From the chemical bonding point of view, you also would see that somewhere this type of a thing is also written. So don't get confused. This is nothing but HiO4 dot 2 moles of water. So the hydrated form of HiO4 is available in the crystal form. So that particular entity is, so what we would be doing with HiO4 or what we are doing it with hydrated one is the same thing. The basic reaction viewpoint would be the same for both of this. Let me do what basically we are going to do in this particular oxidation. So basically, when you treat any any compound which is having onto the adjacent position to OH groups, this is what we call it as glycol. Common name for this, when adjacent carbon are having two OH groups, we generally say it as to be glycol. In other terms, we also say it as vicinal diol. Now the thing you have to remember about this is that when HiO4 is treated with a compound which would have this speciality or this requirement that the adjacent carbon should be having two OH groups, or adjacent carbon should be oxidized in the sense that the carbon which is being attached to the function group would give a carbon a positive center. Just like if this you see into it, here the oxygen is in -1, this is in +1, this is in +1, this is in -1. So the adjacent carbon should be attached to oxygen or through OH bond or through C double bond O bond, something like this also, if this is also there in the starting material. So here what it does is that this first I am telling you the tip to remember or trick to adopt in this discussion. Then we will go into the mechanistic viewpoint also. In this particular reaction, you would not be seeing much of the questions asked from the mechanistic viewpoint, but mainly you would be asked a question from the application point of view. So here HiO4 is being treated. So what you have to do is just take this H and this H, and this HiO4 gave me one nascent oxygen. So this H and this oxygen came out as water. In doing so, this bond get broken. So this is what you call it as glycol splitting. As a consequence, the rest part of the species would change into C double bond O, C double bond O. So this is what you call it as glycol splitting. And what else you taken out is HiO3. So what we can say here about is, this is in +7, now this is in +5. So this iodine got reduced. That is why I am saying it is oxidizing agent. And if I would see critically from the redox point of view, this carbon is in +1 oxidation state. Now it has reached to +2 oxidation state. So this got oxidized. So this is the trick which you have to play with, that adjacent hydrogens are to be taken out as water in this particular case. Now let us discuss first the mechanistic viewpoint, then we'll go into the mechanistic application part of this particular discussion. So what we did is that this I have wrote is the viewpoint of that what basically is H5IO6. Now if I would want to make it that how does it get formed, so for that discussion I have made this slide. So this water attacks it, this goes here. As a consequence, this oxygen would get a negative charge, and this oxygen got a positive charge. Now this oxygen which is carrying a positive charge want to get relieved out of. So this is what you call it as intramolecular proton exchange. So intramolecular proton exchange has happened. So two OH groups got attached instead of this double bond oxygen. And similarly, you just would attack another water molecule into it. If you attack the another water molecule into it, this goes like this. So this also would develop two OH groups onto this double bond O, and ultimately you reach to this entity, this which we are calling it as the crystals of orthoperiodic acid. This I just wanted to tell you. Now coming on to the mechanistic viewpoint. So from the mechanistic viewpoint, if you have a glycol means adjacent carbon containing two OH groups. So what would happen, this lone pair first attacks on this iodine and this bond moves like this. As a consequence, this would get a negative charge and this bond get formed, and here you would receive the positive center. Again, the same sort of entity would happen, intramolecular proton exchange would happen, intramolecular proton exchange, and what it does, this H goes to this negative. And as a sense, now what would you get with the positive charge on oxygen get also relieved, and negative charge on oxygen also got relieved with. Now again you have to do the same thing. This would attack this one, and if I move on to the next page, or you can simply do it like this just to save the time. So this attacks this oxygen would get a positive charge, and just to throw this out, OH negative went out, or you can say it like this also. If you just want to do it in a a little simpler way, this OH negative gone out, just hold on, this OH negative gone out with this H positive, and as a matter of fact this bond comes in between the oxygen and iodine. So what I am trying to say here is that either you just would do all the steps and then throw this out with H positive, or the other way which I just have spoken about is just bring this bond here, H positive goes out along with the OH negative, so water goes out. So this is the entity which you have to little careful about. This is the species which we got with, and now what you are going to do is this bond goes here, 5-membered ring now want to open up, and this bond goes here and this comes back here. So as a consequence, this part of the species, this part of the species got converted into RCR double bond O. Similarly, the other part also RCR double bond O. Along with what you also received is something of this nature. This is also being received. So what basically it is, iodine is in +5 oxidation state. So you just would get a glycol splitting. So this is the mechanistic viewpoint. Now let me do it in a simpler way, the trick which you always have to play with. So we would not be doing every time this mechanistic viewpoint. This is for our understanding, it is fine. Now in the application part, you always have to go with the trick which I am going to tell you. So HiO4 is treated with glycol. So this would provide me one nascent oxygen. So whatever bonds you are going to break, the number of bonds which you are going to break, that much number of HiO4 molecules would be used in the process. So I just would break this bond, and as a result, this H and this oxygen went out as water along with the minus of HiO3, and you just have created a double bond here, you just have created a double bond here. So number of HiO used in this is 1 molecule or 1 mole per glycol splitting is being used. Now if I would move further to give you a little more interesting questions around it. Now you could see adjacent carbons are having OH groups. So now what play I am going to play here with? So this would provide me nascent oxygen. Here now I shall be using 2 nascent oxygen because I am going to break 2 adjacent glycol splitting, which I am going to do. Now what product do we get in this discussion is, so this H and this H along with 1 oxygen would go out as water. So bond get broken. So this changes to formaldehyde. This lower part also changes to formaldehyde, which you can write it like this also, or as a matter of fact, you can also write it like this also. Same thing. And now the point is, what about the other oxygen? This oxygen got added across this carbon to convert this into formic acid, because if you convert this into formic acid, its oxidation state got increased. Same is here, the oxidation state of this carbon got increased from the starting material. So this is the thing which you always have to remember. So here, how many moles are being used? 2. This is very important to remember. Many of the time you would get the questions like this, that you would be given the final product and you would be asked for the starting material, how many HiO4 is being used in the starting material. Similarly, if I would go further for this also, so here also, because there is 1 glycol bond I am able to see here. So this H, 1 oxygen from here, water goes out. Now the story becomes little easy. So upper part would change into acetaldehyde, lower part will change into formaldehyde with the loss of HiO3 along with. So 1 mole is being used here. And similarly, if you just would see into this one also, this bond break from here. So here you would get 2 moles of acetaldehyde. Now the story has become little easier. Now the interesting questions, one more. Now, if in case you would find, let me take this example as well. In this case, what you would get, H, this bond get broken from here, water goes out. What you end up getting here is 1 is ketone, acetone along with formaldehyde. So this is the play which you have to play with. So you would come across some questions like this. You are being given adjacent OH groups like this, and they will ask you something on this nature, that if you are being given this starting material, how many moles of HiO4 is being used. So just see into this question, solve it out, and do let me know what is the value of X in this question. So question is asked in this way, that how many moles of HiO4 is being used in this reaction, and what are the products do you get here with. So I can give you a little hint. This H and this H you take out as water along with, and the corner primary alcohols would convert into formaldehyde, other would change into carboxylic acid. Now what about if the adjacent carbon is containing OH along with CO? Now here you have to be little vigilant about. So here what I would be suggesting you is that in such case you just would take 1 water molecule as one of the reactant, just to make the things easier. What does it mean? That the glycol splitting definitely would happen. Now what shall you then be taking along with? You just have to take into consideration that this HiO4 definitely would give me 1 nascent oxygen, and this nascent oxygen, how the things would turn up. This H, this oxygen, this H went out as water. So you added water got removed out, so there is no loss of water in the sense, and this OH group got attached here. So as a consequence, this would change into carboxylic acid. The lower part would change into formaldehyde. So make it a point how it is to be interpreted. I just have given you a small tip. Water in itself is not used in this particular thing, but this is the way it is to be remembered with. Similarly, if again you would see the adjacent carbons are containing CO groups, so HiO4 would give me nascent oxygen. You have to break this bond like this, and you take into consideration one water molecule along with, just if I would write it once more for you, OH, H. So I just would take it like this. This OH would get attached here, and this OH also get attached here. So you would get 2 moles of acetic acid in this particular discussion. So 2 moles of acetic acid is being used. So whenever, whichever way you go with, wherever you are going to do the glycol splitting, the number of CC bonds you are going to break, that much number of HiO4 molecules would be used in the process. This is always you have to remember with. Now another one, which is again a very important one. So if you are being given this nascent oxygen, just see here, the adjacent carbons are oxidized. So I would break this one, this one. So here also I am going to use 2 nascent oxygen. The corner one would go out as water, and so this, the corner one got out as water. So 1 nascent oxygen I just have consumed with. The other one would join to this carbon. So the corner part would change into formaldehyde, and the center part would have changed into carbon dioxide. So this is thing you have to remember with. Now what about this? So here you use 2 moles of HiO4. What about this one? So here you would say categorically there is no reaction with HiO4. What is the problem here? The problem here is that the adjacent carbon did not have OH group. So this type of oxidation, this reagent would not lead to. So this you always have to remember. So I may say 1,3-diol, or as a matter of fact 1,4-diol or 1,5-diol would not do this type of oxidation. So adjacent OH groups or adjacent CO groups are must for this reaction to operate with. Now another one, this is again very, very important. So in this case you have to see into the fact the adjacent carbon is having one NH group and NH2 group and OH group. This also do undergo oxidation. Now how is it does, how the product and how it is going to happen, just be attentive about it. So one thing I would always say, which many of you people might not have noticed it that way, this OH is 8 plus 1, the total is 9. So this nitrogen is 7 plus 2 in terms of atomic number or in terms of electron. So this entity and this entity are isoelectronic. So you would see many of the reactions generally of NH2 and OH happens in a similar way because of the viewpoint of isoelectronic category they would fall into. Now the point here is how to do this particular reaction. So I again would say what viewpoint we are going to take it here, because again as I said, this nitrogen, if I would consider the NHCN bond, so or CO bond is -1, this is +1, nitrogen is -1, this carbon is +1. So you are going to see the same, that the carbon which is attached to oxygen or nitrogen is carrying a 1 positive charge from that particular bond. So what basically we are going to do in this case is, again this nascent oxygen, this H and this oxygen would go out as water, and you have just broken this bond. So as a consequence, what you end up getting is a imine. This is what you call it as imine along with the formaldehyde. Now make it a point, this reaction would not stop here. This imine always would have the property, because if you would hydrolyze it in acidic medium, this will change into ketone or aldehyde. What I'm trying to say here is that this NH again would have the same sort of isoelectronic species. It is again, nitrogen is 7 plus hydrogen is 1, 8. So 7 plus 1, 8. This is also 8. Now how does it would happen? This thing I have already explained it in many of my videos, that if in case you have with you imine in the presence of water and H positive is given by the periodic acid itself, this would hydrolyze to this entity finally. So how does it happen? This is having a lone pair, this is being protonated. So once it got protonated, so the nitrogen would get a positive charge. Now what I'm doing is, this is what you call it as resonance. So the carbon now would get a positive charge, this is NH2, and this carbon which got a positive charge now is being attacked by the water's lone pair. So water lone pair would attack it. As a consequence, what you would get here is, this would get a positive charge, and here you would get NH2. So throwing out NH2 is a very tough one because it is not a good leaving group. So what you shall then be doing here is that this is called as intramolecular proton exchange. Once you do the intramolecular proton exchange, here you would get with OH, and this would change into NH3 positive. Now what you would do is this bond would go here to create a double bond, and NH3 would go out of the system. NH3 would go out of the system, and the H positive which you added came out of the system, or this H positive goes with NH3 to form ammonium ion that is water soluble and would go out of the system. So this is the way which you always have to remember, that imine would convert into aldehyde. This is always to be remembered. So what trick or tip you have to remember is that if in case what starting material do we have in this case? So what is the final product which we received? We received formaldehyde, acetaldehyde. One is formaldehyde along with ammonia. These are the three things which we have received in this particular reaction. Similarly, if I would go for this one, again the same thing you have to keep it in mind, that what we are going to do in this case, H and oxygen from here, water goes out. First you would generate and glycol bond get broken. So here you would first get imine along with formaldehyde, but this on hydrolysis water and H positive would change into formaldehyde again, and along with the loss of ammonia. So this is very, very important. You always have to keep it in mind. So as I am saying, the application part is lengthy for this particular reaction, but this is for sure something in and around this Malaprade oxidation is always being asked in JEE mains or advanced. Now in this particular case, what we can think about, adjacent carbons are having OH and NH2. So it is a very good starting material for the periodic Malaprade oxidation. So what we would be doing, HiO4, one nascent oxygen would take out this H, and water goes out and this bond get broken. So as a point, you would get formaldehyde on one side, and also you would get imine along with the COH group. This is already in a higher oxidation state. Further oxidation would not happen for this, but this would not stop here. This NH on hydrolysis would convert this into aldehyde. So you would get something of this nature. Okay, I just have taken one carbon. No, it's perfect. So you would get this sort of a species in this particular reaction. So this part change into aldehyde, and this part change into again aldehyde. So this you always have to remember, along with the loss of ammonia. Last but not the least, in terms of carbohydrate, you always have to remember HiO4 would not do any sort of oxidation for a ethereal part. Just like here you have a ether. This is a acyclic ether which is out of the ring, and there is a cyclic ether as well, this one. So although this carbon which is attached to oxygen is having a positive oxidation state in terms of carbon oxygen bond, but ethereal oxygen would not do any sort of oxidation with HiO4. So now you have to be little critical about that, what product do we get in this particular reaction. So I just would see this carbon, and this carbon. These three carbons are having adjacent OH groups. So I would break this bond and this bond. This particular entity would change into, because there is one carbon, so this would change into formic acid, and this particular part would change into aldehyde. This also would change into aldehyde. So what product do I get? So I have to do this in this particular question a little patiently, because otherwise we may end up with wrong answer. So this would get formaldehyde, and this entity would change into formaldehyde. This would remain as such. This would not get oxidized because the carbon here, adjacent carbon, do not have OH groups, and this as such would remain like this along with the molecule of formic acid. So here also number of HiO4 used can be asked in this particular question also. How many bonds we have broken? 2, so it would be 2. So this also you have to remember with. So I almost have done most of the application, and if you just would want to see from some foreign author books, this is the type of mechanistic viewpoint you would come across in many of the Solomon or Morrison Bide. You would find these type of mechanistic viewpoint given in many of the books. Now let us do the questions very rapidly, although the video went in length, but still it is very interesting to explain the things. Which among the following may not, they are asking which of the following will not undergo oxidation with HiO4. So I could see very categorically that this carbon, if you would see, these two carbon can undergo oxidation because adjacent carbon are having NH2 and OH group. Similarly this one also, because adjacent carbons are carrying the OH group. But in the C option you could see that although this is oxidized and there is a OH, but as it is not in adjacent to each other, so this would not undergo any sort of oxidation. And if I have to write the product of all these reactions just for your help, or just to create more question answers in this particular question, so this would break it like this. So this part would change into acetaldehyde, and this part also would change into acetaldehyde along with the molecule of ammonia. So this is the answer for this one, and this is quite easy. If you would break it from here, this is CH3, this is CH3. So H and one oxygen from HiO4, water goes out and you end up getting acetaldehyde and acetaldehyde along with loss of water and HiO3. And what you have added, HiO4. And what about the last one? So here it would break from here. So this CH2, so this H and one oxygen from the HiO4 would convert this into water. And what answer do you get in this particular question is, one is the formation of ketone and another is the formation of formaldehyde. So this also you have to remember with. Now let us see the next question. What is being asked in this question? What is A? So as I said, this also is a very, very genuine JEE mains or NEET examination, or even for JEE advanced this can be asked. That although, okay, let me complete the question. It got deleted because of some reason. So this is somewhat like this. This is the question given to you. Okay, so what basically it is being asked in this question is, you happen to get 2 formaldehyde and 2 formic acid. So it is quite easy that the corner CH2 OH groups might have converted into formaldehyde. So one way is, because I could see there are 4 carbon atoms being formed in the final product. So this is containing 1, 2, 3, 4, 5. So this would be a wrong answer because it is starting material is having 5 carbon, and here 1, 2, 3. So here it is having 3 carbon only. So this also is wrong. In a way, if in case I don't know the viewpoint about this particular question. So here you could see there are 4 carbon and adjacent carbons are carrying the OH group. So it is a perfect entity for the this particular oxidation. And what about the last one? 1, 2, 3, 4. Although 4 carbons are there, but the 2 OH groups are onto the same carbon, so it would not lead to the product which we are thinking about. So what answer do we get? So I think the answer to that question would be the C option. So in the C option, what we are able to see here is that this would go out as water, one of the nascent oxygen, and bond get broken from here also, and the another nascent oxygen would go across to this two. So the 2 nascent oxygen, so one would change, this would change into formaldehyde, this also would change into formaldehyde, and you also would get 2 moles of formic acid. So I think we are on a right track. So the answer to this question would be the C option. Okay, so let me go on to the next question. The video actually has gone in length. Anyhow, in this question, what the examiner is asking, to oxidize one molecule of compound A, this is compound A, number of molecules of HiO4 needed, and how many molecules of formaldehyde is being generated. So what this starting material is, this is the starting material which is being given to you. Now I could see this H and one oxygen would go out as water, and this bond get broken, this also got broken, so you would get formaldehyde, and now you also have to break this bond. So how many bonds you have broken? 3 bonds. So one molecule of HiO4 is already being used, and now I just would take 2 more nascent oxygens. 2 more nascent oxygen. In totality, I used 3 moles of HiO4, and 2 nascent oxygen would come across to the carbonyl group and change this into carbon dioxide. Am I right? So it is perfectly fine. So you happen to get 2 formaldehyde being formed in the reaction on the usage of 3 moles of HiO4 with the starting material, if you have taken 1 mole of the starting material. So what answer do we get? So they are asking us in respectively what is in which order it is to be done. HiO4 used is 3 and formaldehyde being formed is 2. So the answer to this question would be B option. One more question. This is also very interesting. Somebody has sent me. This is a more than one choice question, where you are being given a starting material which is being treated with KMnO4 in alkaline medium, and then it is being treated with X moles of HiO4. The examiner is asking us about X, P, Q and R. Something about R, P and Q and X is being asked in this question. Now let me first do the solving of this question, then we'll discuss what the options are. So this alkaline KMnO4 is also called as Bayer's reagent. Many of you people might be knowing it, and this reagent is also an oxidizing agent, mild oxidizing agent, which converts any double bond into diol. Just if you just would want to convert a double bond into, this is what you call it as hydroxylation reaction as well. If you just would want to do the hydroxylation of alkene, you just would want to attach 2 OH groups onto the same adjacent carbons, vicinal diol you wanted to make. So this is a very beautiful reagent, alkaline, cold alkaline KMnO4. And the addition across this double bond is syn addition. This is syn addition. So along with one question, I am telling you many more things and you should feel happy about it. So other reagent which you can also use is osmium tetroxide followed by hydrolysis with sodium bisulfate. So this also does the same thing. It is a syn addition. And another reagent which you can also use in this particular discussion, which would take the reaction towards the anti-addition, that 2 OH groups got attached into the opposite direction. So anti-addition. So here you would be using the reagent name would be peroxy acid and followed by hydroxylation or followed by hydrolysis. So any of the peroxy acid which you can use is, there are many, but the most important is peroxyformic acid or MCPBA, metachloroperoxybenzoic acid. This is also a reagent of choice when you wanted to convert metachloroperoxybenzoic acid. If this reagent is being added to any double bond, so what first thing you would get along with, I have made a video on this, just see into this particular link shown above. So this goes, this would convert this oxygen into peroxy, and because of the angle strain in this 3-member ring, if you would hydrolyze it, it immediately would open, but the water would attack from the rear side of this and this opens like this. As a consequence, you end up getting the anti-addition. So this also you should remember with. So what basically we are having with us, so KMnO4, alkaline KMnO4, you have to add across into it. So what product do I get here is, so I would get OH here and 1 OH here, and also I do get here, because why I'm adding across the two double bond, because in the answer they have given 2 moles of formaldehyde is being formed from HiO4. So this, in a way, I have to create 2 moles of formaldehydes, and 2 moles of formaldehyde, when I just would treat this with HiO4, 2 moles of formaldehyde would only be formed when this H and this H goes out as water, which we get from the nascent oxygen along with, and the bond get broken from here, isn't it? And this part would then convert into ketone, and this part also would convert into ketone. So basically what you end up getting in this reaction is somewhat like this. You would end up getting ketone along with 1 formaldehyde on this side and 1 formaldehyde on this side. So we are almost through the question and we are able to understand the answer of this particular question. So what basically we are going to do in this particular case is, let me see into it, what options do we have. So here what basically we have, we created a diol and theek hai, it is perfectly fine. So now the point here is what basically we had supposed to do in this particular question. So first x is 2, that is right or wrong, how many moles of, how many bonds we have broken. So I think it is perfectly right, we have broken this much number of bonds. Yes, it is fine. And along with it, what else you do get here is Q is cyclobutanone. No, it was cyclobutanone 2, something like this order. So this is wrong answer. P has 4 hydroxyl group, 1 keto group. P is having 4, this is P. It is having 4 hydroxyl group, but it did not have any keto group. So this also is a wrong one. So this option is also wrong. And X is 2, this is perfectly right. We just have used 2 moles of it. And along with it, what you also do get here is first option. R is, so this is the way it is being asked. That is why more than one choice questions are very interesting. So now here IUPAC naming is being asked. So you are being given this compound, and now this is your main carbon chain. This is your main carbon chain, 1, 2, 3, 4. This is the main carbon chain, and this part would be treated as a prefix. When any radical is attached to main carbon chain through a double bond, then it is to be referred to as alkyladene. Here the alk is 1 carbon, that is meth, so we will be saying methyladene. So what name do we get for this is, there are 2 methylidene. Methylidene is a complex substituent. Bis 1,3 methylidene. At 1 and 3 position you have methylidene cyclobutane. So this is also very interesting nomenclature, where you happen to get wherever you would get a double bond attached to a main carbon chain, that double bond is to be referred to, that subsequent is to be referred to as alkyladene. So this is what we are supposed to do in this. In the last, which I asked in the very starting, that what is Criegee oxidation? Criegee oxidation happened in 1931. The reagent used for this, which many of you people are aware of, this is lead tetraacetate. This is also a reagent of choice to do 1,2 glycol splitting, lead tetraacetate. So if you just would write it like this, lead tetraacetate, or at times you would find this written in books like this, lead tetraacetate is the reagent which also could do the glycol splitting. Just see the way I am doing it. So this H and this H and 2 acetate from the lead tetraacetate would give me 2 acetates. 2 acetate would take up this H, so acetic acid goes out and this bond get broken and you end up getting keto. Here also you would get CO group generated. Along with what gone out is this H with this acetate ion, 2 moles of acetate ion. And what next you would get here along with diacetate. This is the diacetate which you happen to get. So here you may take this as from the inorganic point of view also, that lead here is in +4 oxidation state goes to the +2. So lead which is in +4 oxidation state goes to the +2 oxidation, +4 to +2 oxidation state by gaining 2 electrons. This is nothing but why it has happened, inert pair effect. You can say it like this. But this reagent is a reagent of choice for glycol splitting only of a simpler one. Much of the compounds would not show as it's being shown with HiO4. And if I would just show you the mechanistic viewpoint of this, again the viewpoint would be the same. This attacks this, acetate goes out. So acetate goes out, or in a way you can show it like this also. If you just would want to do it in a proper way, the proper way would be somewhat like this. This acetate went out, this bond get attached here, this you got a positive charge, and now this acetate would deprotonate this H, and as a consequence 1 acetic acid went out. 1 acetic acid went out. Is it okay? And do the same thing on to this side. This would attack it, this acetate would also go out, and once it go out you would get with this entity, and this entity now would open up like this. This is the important one, and now it is not a tough one. On a same pedagogy, we are doing the same thing as we did for HiO4, and along with you happen to get lead tetradiacetate. So this is what you have achieved in this particular reaction. I hope you have understood this particular discussion as well, and if you want to see it from some foreign author book, this type of a content is available, so you can refer to this one also. So there are two oxidations we covered today: Malaprade oxidation and Criegee oxidation, where the reagent was lead tetraacetate. Hope you have enjoyed this particular session. In some other video we will be taking some more named reactions which are quite important from JEE Advanced and JEE Mains examination point of view. Thanks a lot. Have a nice day. Stay safe. Take good care of yourself.